My clock here on Microsoft time says 3:59. So does my cell phone, which I'm gonna shut off. Okay. Today's topic, although we touched it last time a little bit, today's topic is hydro scheduling. And you'll see that in a minute or two here that some of the topics, some of the techniques are very similar to the ones that we used in the fuel schedule, where we were scheduling gas or oil or something, or coal. But hydro has a unique history. I'm going to show you some pictures, and I'm going to send all these along inside the problem session thing today. Let's see if we can capture most of that. Largest hydro plant in the world. Those of you that are in the class that are from China recognize this as the Three Gorges plant. 18,200 megawatts. 18,200 megawatts. Now I'm going to reveal something about my personality. When I was in when I graduated from my undergraduate years, I was thinking I would do a career in computers, and I had been a student intern, or we call it a co-op program, with none other than IBM, and I honestly didn't like it that much at IBM. I got bored at IBM. But lo and behold, there was an article that IBM put out talking about the use of an IBM, what they call a process control computer, to help run and operate the American Electric Power System Control Center in Canton, Ohio. Now, that interested me very much, and because one part of me loved the electric power systems. And I want you to look at this picture. I don't know how big that Three Gorges Dam is, but it looks enormous to me. And if you were to start here and start walking, I'll bet it's a couple hours to walk across this thing, maybe longer, assuming there is a walkway that you can get across it. Power systems, the facilities are big. And to my mind, that's engineering. I don't get my kicks out of engineering some integrated circuit that's a half-inch square or a little bigger. I don't get my joy out of engineering something that's on a printed circuit board 2 inches by 3 or 4 inches. I like to see great big facilities like power plants. My father was a civil engineer. That's the kind of thing that civil engineers do. So that was a way for me to do some work in the power field, where you have big facilities, and then you have electrical engineering. Here is the Tidepool hydroelectric plant. It's on the Parana River in Brazil, between Brazil and Paraguay. Tidepool is 14,000 megawatts. 14,000 megawatts at one location. Of course, Three Gorges is even bigger. I want to say, just for example, for many countries of the world, hydro represents one of the first ways that they can get into to building an electrical infrastructure, because number one, it provides an impoundment, a reservoir behind the hydro facility. In the case of the Tidepool, here's the dam, or what we call the part that impounds the water, and the water is up behind there, and that provides water for irrigation, for drinking, for whatever, and it also is a way of controlling floods. A lot of the American hydroelectric plants in Tennessee and out in the state of Washington and Oregon on the Bonneville River were done for flood control. Without the dam without a series of them, the water would overflow its banks often enough that you couldn't really develop the land adjacent to the river without worry that any properties that you built would be flooded and destroyed. So it's an infrastructure that's good for, and then you put a powerhouse there with hydro turbines, and you can generate electricity. So, as I said, for a lot of countries, that was the initial way. Now, here's probably the biggest in the United States, called the Grand Coulee Dam. This is part of Bonneville Hydro, the large government-owned, and you can see that. Here's I don't know which was the original and which was the additional. I think this was a powerhouse added. Anyway, it's a huge dam, and this is all the water it's got behind it. Grand Coulee Dam, but it's 6,809 megawatts out of Grand Coulee. So these facilities, now within a country like the United States, pretty much the hydro facilities have been developed. There may be some very small facilities that they can still develop, but whether or not they're economically, advisable to do it. So wherever there's been a place where you could build an impoundment, build a dam across the river and start generating, it's already been done, and that's probably the case in most of Europe, most of, for example, Norway, which generates all of its energy, all of its electrical energy by hydroelectric. And pretty much, I would say that's the case for Europe. Now, Canada, there probably are still some places that they can develop up in the northern parts of Canada. I don't know for sure, but Canada has developed a lot of hydro. In fact, in Canada, a lot of the power companies used to have the name hydro. In the eastern part, you had the huge in Quebec. You had the hydro company there. Hydro-Quebec is what was called. That was the first word, was hydro. Hydro-Quebec. Next to the west is Ontario, and it used to be called Ontario Hydro. It now has a completely different name. All the way over to the western side of Canada to British Columbia, and the power company is BC Hydro. They use the two letters BC Hydro. So Canada has exploited their hydroelectric to a great advantage, and the U.S. benefits from it because we can buy energy from Canada much cheaper than we can generate it, because they have sufficient hydro energy that's available they can sell. So the idea is that you have some sort of dam across the river, okay, and there's inflow coming in. Here is what we call a reservoir in here, which has a volume, and that volume, I'll just call it back. So there's a volume min, there's a volume, and a volume max. So you don't want to run it. You can't run it up too high. Although incidentally, if you push the volume up too high, the water goes over the dam like this, and they call that spill. Think about this. It's not too hard to realize this spill represents a waste, so to speak. It's a waste because it's water that could be used to generate, and we'll assume that they run what's called a penstock. It's a great big pipe down into a building that has a shaft like this, and here is the turbine. Now we're going to see in a little while that I'm drawing a Francis turbine, and the water comes down here and comes out. Penstock here, and this is the so-called tail race. The amount of drop, okay, the distance that the water drops here in has been given the term head, and so you'll hear me talking later on about high head and low head and so forth. Is the head, and obviously the greater distance that the water drops, that's the water gives up potential energy to gain kinetic energy, which it then imparts to the turbine. Now notice that the turbine here, the shaft is vertical. The shaft is vertical, as opposed to a steam turbine. Let's move the paper up. So this is hydro. Here's a steam turbine with steam coming in under high pressure. Well, that steam is moving much faster than water, but of course the water is heavy, and there's an enormous volume of it moving. But this goes into to turbines in here, and these turbines, the shaft is horizontal. So here's the blades and so forth, and we push steam through it, and they rotate like this. And then here's the generator, and we'll put three wires coming out, A, B, C, our three-phase AC coming out of the generator. So hydro, the shaft is vertical. Also, the shaft here moves much slower. This one could move at, let's say, 1800 RPM. This one will move at much slower, some fraction of 1800. We're dealing with a 60 hertz system, and so 2-pole or 4-pole. We can talk about that at a later time, but well, it's just a 2-pole generator would have a shaft like this, and it would be rotating. Here's north, here's south. There's a DC current going around, coming out here. Here's DC, and so we get a north-south magnetic pole. And if I have a set of coils out here that represent phase A, we'll call that A prime. Well, the North Pole passes it, 60 hertz. How often does it pass it? It passes it 60 times per second times 60 seconds per minute. So at 60 hertz, this would have to operate at 3,600 RPM. 4-pole looks like this. There are magnetic poles like that, and they go north, south, north, south. And here's the shaft, and it rotates. Here's the A phase, and here's the A phase, A prime. Well, now you're going to every rotation you get a north, a south, a north, a south. So you get 2 cycles. So this actually, for 60 hertz, this goes 1,800 RPM, revolutions per minute. Okay. If you're doing this with a hydro turbine, you might have 24 poles. Okay, so do the math. If to just go to 2-pole, how much we got a reduction from 3,600 to 1,800? This comes down 24 pole or more. Then this is spinning, and again, this shaft is going like this. This is going like this, whereas this one is going vertical, and it's much slower. It is much slower. The first powerhouses, interestingly, the turbine was way down in the basement, so to speak, and the powerhouse was up at the level of the top of the reservoir, and they had these enormously long shafts. They don't do that anymore. But these hydroelectric facilities are, as we saw, are very big. Now I want to talk very briefly about the types of turbines, because this may come up sometime in your reading or doing some research if you're looking. There's the types of turbines. There's what we call a Pelton, and the Pelton is an impulse turbine, and they have a wheel, and they have these things that the people will describe them as spoons. Obviously, they're bigger than a spoon, and they will have a pipe coming in, and then they'll just have a nozzle, and the water comes out like this and pushes against it. Okay, and then it causes it to spin. These are used for when you have high pressure due to high head. Okay. So if you have water source that's impounded on the top of a mountain, and you're running a pipe down the side of a hill, that's the type, and it looks like this. These are these spoons, and the water will hit like this and then spray out, but it'll impart kinetic energy to the turbine. This is a picture, a diagram of you got some reservoir up here, and then you have just a little bit, but then you have a big drop down to, let's say, a river down here. And it's high head, and it's not that much volume. Then a Pelton is the ideal efficient. People worry about. I was at a conference in Norway where there's actually a hydro institute at I'm going to call it the Norwegian Institute of Technology. It's actually a little bit different name now, but it's a hydro institute where they have hydro turbines, and they actually experiment on the shape and optimize the shape. So you want to worry about efficiency. Now, the next type is a Francis turbine, and the Francis, if you see this picture, the water would come in the other side here and then come out. down here, and so the water is flowing, and it's actually fed all the way around into a chamber above, and then it flows through this, and you can see how it would push it around like this. Here's a different picture at the top. It's called a reaction turbine because the water is flowing, and an enormous volume of water is flowing, and you notice that the blades, so to speak, are tipped like this, so the water goes down, and the water is going to push it to this way, and it rotates like this. They said in this article the largest single turbine could produce 750 megawatts. That is a lot of power. 750 megawatts out of one of these Francis turbines. So this is the type that you would be using in Tidepool, Grand Coulee, or of course at Three Gorges plant. And the last, so this is the largest 750 megawatts reaction turbine. The last type is called a Kaplan. Oh, let's get it right. Kaplan turbine. And this is for low head, large volume, and typically what we call run of river. Let me do some artwork here. What do you mean by run of river? Suppose I have a river. Here's the bottom of the river, and I have a dam across the river, and the river just flows like this. So I can put one of these facilities in here to funnel the river water into it, and this guy looks like just looks like a boat propeller. Really, it just looks like the propeller of a boat, and it rotates horizontally. Okay, the Francis is vertical. Pelton and the Kaplan are actually horizontal shaft turbines. So then you'd have a generator in some sort of enclosure, and the river would just go through it. And so you get a lot of water going through there. You don't have the ability. Maybe you don't have high cliffs, so you can't really build a big high dam. What you need for a big hydro facility is you need it to go through a gorge where you can build a dam. And when you build the dam, it just fills that up and backs up a lake out behind it. But if there's no way to do that, well, you can still get some generation, but as long as the river is flowing like that. Another very interesting one is tidal power. Here again we have our river, and we have a dam like this. Only let's say that during, I'm going to build this a little higher. During the high tide, the water comes in, and it fills this to this level, high tide. And maybe I generate as the water goes in. So here's my shaft, and I'm on the shore, and I'm generating as the water goes in. Then what I do is I close the dam off, and I let the water go out. So now it's at low tide. Now I have some difference, and I can funnel the water back. So sometimes the water is going this way, and sometimes the water goes this way, as I'm demonstrating with the red pen here. So the water is coming back out. What this has is the ability to change the pitch And so you have a shaft, and you can let's get my hand in the right place. You can shift the pitch as you can on an airplane propeller, as you can on on wind turbine propellers up in the air. Same thing with these Kaplan blades. By changing the pitch, it still rotates in the same direction no matter which way the water goes. You don't want to reverse the generator, because then the phase order, if it's a three-phase generator, the phase order, everything gets messed up. You want it to always rotate in the same direction, but the water can be going one way and back the other. Okay, so that's a little bit about the physics, not the physics so much, but the physical aspects of the turbines. You'll get all of those in the notes. In addition, I'm going to give you some tables that I pulled out of some database. Someplace you'll get these tables like this, which will tell you it's got location and longitude and latitude if you really care to know. But China, Three Gorges, 18,000, Tidepool, 14. Goree Dam. Anybody here from South America in the class? Goree is in Venezuela. I don't even know anything about that, but that was considered one of the biggest hydro facilities in South America. It's 10,200 megawatts. There's one called Tidepool Dam. It's in Brazil. And then we talked about Grand Coulee. So there's a couple more great big ones. Later on, we'll talk about pump storage. But here's some of the run-of-the-river dams. They're not up in the 10,000s. They're like 2,600. There's one in the U.S. at Chief Joseph. That's another one that's on the Bonneville. John Day, also U.S. Canada. There's one down here in Pakistan. Of all, let's see. Of all, it's 1,400. Tidal power is on here. You can look at these, and so those statistics, that data is part of the information that I'm going to put on the internet for you. All right, so let's start talking about how we schedule the hydro and okay. We've already drawn this, but I'm going to just to put everything on here. There's V sub I. There's the inflow, R sub I, and this is all of T. Inflow. This is the volume. Spill, if there's any spill, this is facility I. Here's our hydro facility, and we're running water through, and out comes Q, sub I of T, and this is the outflow, and P is a function of Q of T. You can write P of Q. We most often will say, well, what is the outflow as a function of the power going out? And there's a reason we do the inverse, that we're more interested in it. What is the Q for a certain amount of P? And we'll actually draw a curve that way. Now, for most hydro scheduling, we would have a hydro plant, and let's just say right now that we have a steam plant, and the steam plant produces P of S, and of course the hydro plant is producing P of H. Let me put an H here, pH, and that's the hydro is putting out pH, and of course PS plus pH equals the load, P load. So what are you trying to optimize? If there's no steam, what are you going to do with all the all your optimization techniques? And so most hydrothermal scheduling is really hydrothermal. Whoop. Hydrothermal, and essentially that's hydro and let's just say thermal power. It can be coal, gas, oil, which is not that used anymore at all. And the optimization says minimize the thermal cost. Minimize the thermal cost with hydro. So we still do economic dispatch to worry about the minimum thermal cost among the thermal plants, but we also want to schedule the hydro so as to minimize the cost of operating the thermal. Now suppose, on the other hand, suppose that you're Norway, for example, and suppose you have an all hydro system. So there's no cost to minimize against. Okay, I don't have an objective function that says minimize the sum of the thermal costs, because there aren't any, to my knowledge, and I think I'm right. Norway does not have any thermal power plants. They don't have any gas turbines, although they've got a lot of natural gas that they bring in from the North Sea, and they have wells that they've constructed out there on platforms in the North Sea, and they bring those they bring the gas in, and they just pipe it down to Europe and sell it. And so they're always selling natural gas, and they sell a lot of electricity, which comes in through high voltage DC connections into Europe. So what are you doing on all high? Well, here's one thing: make the best use of the water. What does that mean? Well, don't set it up so that we don't want to spill any, and we'd like to be generating with the hydro as much as possible all the time, making the best use of what water we have available. That gets into a different set of issues. When you have a hydro system, whether it's a hydrothermal or an all hydro constraints. Of course, there's the spill over the dam. Remember, I said that you can have spill. Now, the one thing about spill, if the dam has got too much water, it's right up to the top, you want a controlled path for that water to take. If you don't build a controlled path, then you're in trouble, because let's say here's my river and here's the dam down here, either you spill it and you have spillways right over the top, and you may have gates that can go up and down here that are up in the top here. They can go up and down. And then it comes down and into the river in a nice controlled way. Or what they will often do is they will construct a cement or whatever pathway around the dam, and at a certain height they will open this and they will let the water come around this way. You want to be able to control how you spill the water. Otherwise, it's going to start running down wherever it can find a path, the lowest elevations. And if it's just running over the dirt, it's going to be digging up the dirt, and pretty soon the dam will fail. Because you didn't control the spill. You didn't arrange a place for that water to go. So you'll see pictures of hydro facilities with they didn't want to put a spillway on the top, so they put a spillway, call it, around the top, around the side, so that they could make sure, okay, if there's too much water, we can't generate, but we're not going to let that water destroy the dam and send a flood down the river to kill people and destroy property. All right, but there's more. So we said. We said that we're talking about constraints. So we said spill is one of them. River levels. River flow. So the levels, you don't want the river, if it's too low, then no boats. If it's the Mississippi River, then you can't run barges up and down the river. So they never let the Mississippi get down too low. If it's too high, you're getting flooding. So if it's too high, you get water going over the side of the bank of the river, and it's going into towns and destroying property. It's rushing the water across farms and just digging up anything the crops. River flow is very closely associated with river level. But a lot of these hydro, I said earlier that a lot of the hydro plants are part of an infrastructure dealing with water for irrigation. And you need to have enough water, usually by law. States in the United States or the federal government will pass laws that say don't operate the river without at least this much water going down the river every hour of the day, because all along the river there are channels where they can lead water out into the fields to irrigate crops. And believe me, in the U.S. anyway, I'm sure this is true elsewhere, the fight over water is an enormous one that takes years and years of litigation and political, as we say, political wrangling, political arguing and fighting. So the river flow, reservoir levels. Reservoir level. So here's our impoundment here. Well, suppose I get it really low, so it comes down like this, because I'm using up all the water to generate with. Well, you know what happens? The water starts to recede from the shore, and people built their summer cabins. This is actually true in Minnesota. Everywhere where they build their cabins on the shore of a lake, and then if the lake level goes down, they have to pull their boat out before it gets too low, because the boat will be sitting on rocks, or it'll be hitting rocks as it's moving through very shallow water. There is a lake, I don't remember the name of it. There's a lake in northern Minnesota that was specifically built to control the water level on the Mississippi River. And in 1988, I was living here. We had a drought. We had a fairly bad drought. We had months and months without any rain. And the level of the Mississippi River was getting dangerously low. So they warned everybody, but they started draining the water out of this lake. That's what it was built for. People had built cabins on the lake. They had docks out into the water, and they had their boat. And they immediately went to court and says, you've got to block it's called the Corps of Engineers in the United States that runs these rivers and so forth, that manages them. I got a laugh out of that, because these people thought that they had the right to dictate that the water level be high enough for them to float their boats and go fishing and go water skiing on the boat. Even though this particular lake was built and was dammed up so that it could supply water under low conditions. But that's another reservoir level. There's even a legal term in the United States called riparian rights, which are the rights that people have to irrigation water and to boats and so forth. So you've got river levels, no boats. This up here is shipping. If the river levels get too low, reservoir levels get too low, it's a problem for boating and so forth. Obviously, so you've got it's an enormous problem. Ideally, what you'd like to do, let's say we have a mountain range like this, and then we have and it goes down like this. And up here in the mountains, we've got a river that's let's say that's coming. There's a river that comes down and down and down, and it in days gone by, we build a great big reservoir up here on the river, and then we build another one, and then we build another one down here, and pretty soon it gets to be pretty flat. But I have these reservoirs up here, and they will manage this so that they will say, I'm gonna have enough water in these reservoirs to keep the river flowing, even if I have a disastrous drought over a period of time like 5 years, 5, 8, 10 years. Long. So their time horizon, their schedule can go out 5 years. On the other hand, if they have they have the winter, and they have lots and lots of rain. This is rain coming down. It doesn't look like rain. These don't look like clouds, but you have rain or snow, huge amounts of snow, and it builds up what they call a snowpack, and then in the spring it starts to melt. If I have a great big reservoir in here, they might be able to keep most of the water for the whole year, or for a couple years worth. They can fill up a great big reservoir. Now look at the advantage. Let's say that they have large amounts of snow, and they just run just a little bit down, and they let this thing fill. So they're letting it fill up. The next year, same thing. They keep letting it fill up. Having a great big reservoir up here means that I can control the flow going down the river. I can meet the boating needs, for these boats, these barges. Here's the barge, and it's pushed by a little tug here with a little stack on it. That's being barge traffic. irrigation where it's coming off, pleasure boating on those reservoirs. So having a large reservoir high up or way up on the near the water sources, near the mountains, is a big advantage, and it's a major. If you look at there are books, there are entire books written about just managing hydro resources like this. Okay, this course is not about managing a river system. It's not about that. It's about how to make the best use of the electricity versus the rest of the system. Okay, but this is a topic that economists and or civil engineers and so forth would study. Is the hydro resource management. Okay. We can solve our hydro problem. Again, we have a thermal plant with an F of PS for the steam. We have a hydro facility over here with a Q of pH, which is the hydro facility, and we say, okay, the Lagrangian. This is going to look very familiar for T equals 1 to T. N is the number of hours in each time period. F of PS of T plus lambda T. P load T minus PS of T minus pH of T. And then I have our familiar gamma times the sum T equals 1 to T, N of T, Q of pH of T minus some Q total that we want to shoot for. So it's the exact same situation, only here we're talking about a Q total or a certain volume that we want to run through the plant in a certain time period. And we then operate the hydro plant to minimize. So we're minimizing the sum. Actually, there should be we can put another here. We can say I equals 1 to N. So we could put an I here. Fi of PIST, which is the steam plant. So I'm minimizing the cost over all the steam plants here. And that is that's basically the same procedure, the same problem as we had in fuel scheduling. And we take our derivatives, we solve this by doing the derivatives just the way we would have formerly. Okay. The problem with this, if you looked at the CUSP lecture, you saw this, and I'm not going to go into it in great detail. But the problem now comes when I have a reservoir, and I have another one, and then I have another one, and I need to operate all three. So now I got a Lagrangian as the sum of over the I equals 1 to N of the N of T F PS of T. So this is my thermal cost minus plus lambda T P load minus PS minus pH, just like before. But now I have pH 1, so here's 1, 2, 3. And I have Q coming out of each one. So there's a pH 1, pH 2, pH 3. I have 3 different hydro plants. And what I'm going to say now is that I have a certain volume, V1 of T minus V1 of T, let's see, this is T minus capital T. So it says over the time horizon, what's the change in the volume on the plant, and it's equal to minus the inflow into the plant minus the spill. So this is inflow, spill, if you have any, minus Q of pH1 times NT. Boom. So that's lambda 1. Then I've got lambda 2 times a similar constraint plus, gamma 2, gamma 1, 2, and 3. And so now, this should have a plus sign here. I can't use the techniques that I used when I have a single gamma where I just guess a value and then adjust it up and down. How do I adjust the 3 so that I get all 3? And these two are just like this, only they're written around the second and third reservoir. How do I get this? How do I adjust these gammas? How do I do that? That's the, if you just apply the Lagrange method directly, that's where you end up. It doesn't work. You can't do it that way. You can't find the gammas. Unless it's very restricted problem maybe, and you've only got a very narrow range for some of those, and then they just take a little smaller. But even then, that technique doesn't work. So we're going to have to do better than that, and we'll talk about that next week. But the solution is so adjusting gamma 1, gamma 2, gamma 3, etc., up to however many hydro plants is a no. It does not work. Does not work. This does not work. We're going to investigate in the next lecture on Tuesday next week the use of dynamic programming, which can be used for hydro problems very effectively. Dynamic programming or linear programming. And you may have discovered, and if you haven't, I'll be telling you over and over again that my favorite is linear programming. Once again, if you're going to get into this, learn linear programming. Take a course. There's courses on the campus that cover linear programming very well. There's one in our department, electrical engineering. There's one in system engineering over in mechanical engineering, and so forth. Incidentally, I sent an email out to all of you today that talks about some summer internships at Argonne Laboratory, and guess what? It's for optimization, for resource scheduling. That's what we're covering here, people. All right, I'm going to jump to a different topic right now and try to cover it in the remaining time, and that's pumped storage. The idea of pumped storage says I build a reservoir someplace on a bluff overlooking a river or overlooking a lake. So here's a reservoir. And down here I've got a river. And so I impound this and I run a pipe all the way down here where I have a powerhouse, And I have large turbines and generators. But these generators are special. The generators can be run as motors. So, if this is full of water, I let the water come down like this. And we simply say that that's the generate. So we're running it down, and it comes down through the generators into the river. And it drains this down. This thing gets less and less and less. So once this is full, I can generate for a certain period of time until this empties. This does not have a river running into it necessarily, and but it's higher. It's a large drop. Then at another time of the day, I reverse. So I can reverse the generator so that it becomes a pump. Now what they have to do is they have to use air pressure to push the water out of the turbine, and then they can start the generator and they can start it spinning, and then they can gradually let water in, and it pumps water uphill. So, pumped storage. When you want to store energy, let's write pump here. When you want to store energy, you pump. And notice that pumping requires that you buy electricity, or that you use electricity. Pump. Use power from the system. Generate, we supply power into the system. Use power means essentially that I'm buying it. I got to buy it from somebody. Even though it's my own system, I got to generate it at the steam plants. So I'm going to use some power to pump the water up, and then at some other time when I'm needing it, I turn this off and I open the gates back and I let the water come down and I generate. So it can be a pump generator. Usually in the generate mode, it can go up and down. The pump, it goes on and it has to pump at a specific fixed level. It doesn't. You don't vary the pump up and down at all. It's fixed pumping, and you run it for a certain amount of time to fill this up. Now it turns out that this kind of thing is, if you want to store energy, people have been working on energy storage is a huge energy storage. What are some of the methods? Batteries. Mr. Tesla's company out there, whatever his name is, the Tesla is an example of that. Flywheel. Compressed air. All of these are little bitsy, here, I didn't move this up. I'm sorry. Let me go back over this again. Energy storage. Batteries, such as Tesla. It wants you to buy a big battery and stick it on the wall in your house, and then if you have solar cells, you can charge the batteries, okay? But batteries are a way of storing energy. Flywheels. You take electricity and you get a heavy flywheel spinning very, very fast, and that has energy in it. And then you can take it back out by letting it slow down. compressed air, you run a pump and you compress air down into the ground. Later on, you let the compressed air come back up through a turbine to generate electricity. So there's a two-way street. Other than the compressed air, especially batteries and flywheels are very small compared to pump storage. Pump storage, I can build a facility like this. We have a table in here that says that the U.S. Pump storage. Let me just put 27. Pardon me. 2,700 megawatts. 2,700 megawatts. I assure you that nobody's going to build you a 2,700 megawatt battery for anywhere near the cost of building a pumped storage. Batteries are good for a small fraction of this. If they're good for 20 megawatts or 5 megawatts or not even megawatts. Same thing with flywheels. Compressed air is big, but it's not on this scale. So energy storage, the pump storage is the only real large means of storing energy that we have. There is lots and lots of research. If somebody someday invents a means, there was something called flow batteries, where you had tanks and you ran these things, these electrolytes through, and you charged them up. It was supposedly a method that would scale up, and then it turned out it didn't. So, if you can ever get something that can store hundreds and hundreds or thousands of megawatt hours into a storage facility, you change the whole game of electric power. All right, so pump storage. Here is the secret. Secret of operation. Buy power at low cost, sell back at high cost. Typically this would be nighttime, and this would be peak daytime. Why does it work that way? Well, it works that way because for the most part the power systems, the cost of generating looks like this. Even for a single generator, but if you aggregate a lot of generators together, okay, it turns out that when this is total generation down here in megawatts. And this is just the F thermal. Well, if I'm going to buy energy, then I want to buy a certain amount of energy down here. So I'll add to the load this much for pumping, okay? And when I add to it, this is the cost. It just gives me this much of a cost increase because the incremental cost, or the slope down here, is very low. I can add load at low load. So this is nighttime load. I can add some load down there. It's not going to change very much. So I can go out and I can buy the energy at night really cheap. So I fill my reservoir up and I fill it cheap. Now so that's the pumping side down here. Okay, so I add to the load. Now when I come back, Here's the daytime. Here's the peak load out here, and now I'm going to generate. And let's say it's the same thing. Now it turns out with pumped hydro, it's not so much that I can't get the megawatts back, but I can't get the megawatt hours. There's an efficiency loss, roughly 67%. So for every, let's just rate, for 100 megawatt hours in, I would get 67 megawatt hours out. Just due to the losses in the pumping and generating process. Still, that's very good. And so here I'm pumping, and now I'm generating, and I'm coming to the power system, and I'm going to say, look, I'm going to turn my generator on. How much is it worth to you? And the operator says, well, wow. If you turn on here, so this represents a cost, and this represents a savings. In a savings of dollars, this is the cost of dollars. So it costs me a little bit, then the whole system goes up the curve, and now I generate with the same megawatts coming back. I get a much bigger savings, okay? Even though I don't get all of it back because of the overall loss in efficiency of the pumped hydro plant. So there's an interesting problem. I think what I'm going to do is I'm going to have to. I think I talked too much during this hour here, but I think I'm going to. I think I'm going to put the problem into the homework, which I haven't posted. I'll post it tomorrow. But the problem that will be like this. You're given and so this is F. This is the F of T here, FT. And so you're given FT is 250 plus 1.5. This will all be given to you in the homework. Whoop, times P S plus PS squared over 200, and that's dollars per hour. And this can go between 200 is less than or equal to PS is less than or equal to 1200. So this is quite a wow. That's not that big a spread. And then I have a pump storage facility. I have an impoundment, and I have a pipe like this. And here it's either generating or it is pumping. And we tell you that the maximum output of the generator is generated as 0 to 180 megawatts. And we tell you that the pumping is 200 megawatts fixed. Although there are two units, so it can be actually either 0, 100, or 200. 0 meaning it's not pumping. Okay, whereas the generator, I can vary it all over the place. And the reservoir storage capacity is 1,600 megawatt hours. So I can pump until this is full, 1,600 megawatt hours, rather than worrying about acre feet of water and how much water per pump. I'm just going to say that the pump, the reservoir is got megawatt hours up here, so I could pump this up. So if I pumped at 200 megawatts, what would that be? It'd be 8 hours, pumped for 8 hours at full 200. I'd fill it if it was empty to begin with, I'd fill it. And then I could run it back down up to 180, and you can do the dividing there to see how many hours of power I would get out of it. And it's got a, so this again is the pump storage homework problem. Would have a load that goes 600, 1,900, 500, 400, 500. So it's at 600, 1,000, 900, 500, 400, 500. And we're going to assume that the reservoir is full at the start and must be full at the end of the day. And so if it's full at the start, you can do a little bit of generating here. You'd like to do a lot of generating here because this is when the cost of the thermal is going to be very, very high up in here. You're going to use a lot of your costs, so you want to generate here. So we'll put generate in here. So these time periods we're going to generate, and most likely we will pump in these periods down here. Okay. And what they want you to know is to get the optimal schedule. Okay. I will give you some instructions with the homework how to do this problem, and it's fairly simple. And we do what we call a gamma lambda. We adjust the pumping and we adjust the generating in every step in order to minimize the cost. That's a very simple pump storage hydro scheduling problem that we're going to run with today. We're going to put that into the homework, and you just do it by a series of tables. You can do it by hand. You don't need a computer program. If you want to write a spreadsheet, that's fine. You can do it that way, and I will put some more instructions on how to do this this type of scheduling. Last of all, I have to show you another picture because this is close to my heart. I grew up in New York State, in the U.S., in the city of Buffalo, New York, which is very close to this, which I think everybody in the class that's from the U.S. would recognize this, and I expect that all of you have heard of Niagara Falls. Well, I live close to this. I live within, let's say, 20 miles, 25 miles of it. And we visited it a lot when I was a kid. Anytime company would come from who knows where, let's go show Niagara Falls. So we'd go to Niagara Falls. This is the American Falls. This is called Goat Island. It is all American. The border between the U.S. and Canada runs down here and then right down the middle of the river. This is Canada. This land here is in Canada, as is this land over here. This is the United States, and the border, as I say, goes right up on that side of this island. This island just ends up here. That's called the Canadian Falls. This is called the American Falls. This is also called the Horseshoe Falls because it's actually shaped like this. It's rounded. And a lot of the U.S. first hydroelectric facilities were built. There's a picture. You'll get a picture of this. Right there, there's a picture of a building. Guess what they had in that building? Well, the Niagara Falls facilities on the Niagara River, obviously, which is water that comes all the way from Lake Superior through Lake Michigan, not Lake Michigan, Lake Huron through Lake Erie, and it flows from here's Erie, Lake Erie, and it flows into this Niagara River And there's an island in the middle of it, so there's one path around like this, and there's another path around like that. It's called Grand Island. And right here is the falls. Here's the Horseshoe Falls. Here's the American Falls. And so here's the falls, and then the river keeps going. So here's the falls. And way downriver, it bends a little bit, and then it goes out to Lake Ontario, out here. What they did is they constructed underground, two underground enormous pipes. I mean, 60, 80 feet in diameter, and they built a dam right here. And the Canadians managed to get water around their side, and they built a facility like this. So here is what you see downriver, U.S., Canadian. The U.S. and the Canadians cooperate on all these things because it's to both countries' advantage. This is called the Robert Moses plant, Sir Adam Beck power plant. Big, huge plants, thousands of megawatts. Well, one of the reasons I want to mention this is that this plant, the Robert Moses, here's the river, here's the impoundment. So and there's water that comes into the forebay back in here. And then they built another thing in the back, which is pump storage. And you could take water, and you could take it at night into the pumps and fill this reservoir. This was a reservation. The reservoir was on an American Indian or Native American reservation for the Tuscarora Indians, and they would fill that up at night. Then, so here it is pumping. Now watch this. This is the part that is so unique. When they generate once, like this, and then they generate again. So any water that they've stored, they can generate it at this Tuscarora plant here, and then they run it back down a little further, and then down into the river. So they get double use out of it. I remember realizing this when I was in college, reading about it and thinking what an ingenious thing to do is put a pump storage plant behind a conventional down here. I'm talking about it and you're not even seeing it. I apologize. So this is the Tuscarora pump storage, and so you take water from the upper part, pump it up during the day. You generate, run it back through the forebay, and generate again. So you generate twice with it. And they showed me their schedule once I was talking to their engineers, and they fill this up over the weekend. That's how big it is. And then they will generate a little bit during each night or during each peak period during the day, and it'll take all week. So it's a weekly pump schedule, pump generate schedule. Okay, we've taken a little bit of extra time. Thank you for indulging me for that, and we will be putting up the homework, posting the solutions at the end of the day tomorrow, as well as putting up your homework for next week. Okay? And we will go off the air here. Good night.